system. Power system in the sense distributed energy resources. That is one of the key term in this GYAN course. So I am choosing wind energy conversion system. At the output of this generator which is connected to the turbine, that is going to be AC, and finally it has to be connected to the grid which is also AC. So then there is an interface between two ACs. One AC could be 40 hertz depending on Vayu Bhagavan's capability, wind power, and then this has to be 50 hertz or 60 hertz. Right? So in between there will be an interface. That interface is a frequency converter. At any stage, if it's not clear, you please interrupt. I will start from very basics. In case if it is not clear, you please interrupt. Whatever is not completed, that I will continue tomorrow just after lunch, 2:15 tomorrow. So I will. This is the overview of presentation. Little bit of introduction on wind energy, turbine, then generator. There are so many generators available. Which generator will be a suitable generator for this application? And then power electronic requirements and some control, field-oriented control, which we have seen popularly as a vector control in case of machines. So similar thing we will see here. This is just to tell that different countries are focusing on renewable energy, wind energy, so that we can get rid of this environmental pollution. But there are other issues like making turbines. Although wind energy and solar energy is considered to be green, actually speaking it may not be green. Kind of a disposal of this PV panels, that's a big challenge. And then once again, making the turbine blades, especially the blades, that also leads to a lot of environmental pollution. So unless the material science engineers come up with the different ideas wherein all this manufacturing and disposal can be taken care, then only we can call it as a green. Right now, I cannot categorize it as green. Only thing is there is no pollution when at the time of generation, but there are pollution in making a turbine and other things. The first graph tells about the variation of the power that we can get out of wind power and with regard to the turbine blade orientation. Tip speed ratio in the sense ratio of two speeds. One is the speed at the tangential speed at the turbine blade and wind speed. Wind is coming like this, but what is the effect on the tip of the turbine blade? So that is called tip speed divided by wind speed. So if that ratio is somewhere around 5, so then you will get maximum power conversion from wind to mechanical, wind energy to mechanical energy, or wind power to mechanical power. Basically, turbine is a system which converts dash energy associated with something to mechanical. What we can put there? Turbine is a system which converts energy associated with dash to mechanical energy. What we can fill up there? Wind, water, steam. So can you think of one term covering all this? So Anji? No. Wind, water, steam turbine, gas turbine, wind turbine, hydro turbine. Fluid. So turbine is a system which converts fluid energy to mechanical energy. The shaft of the turbine is connected to a generator. In some situations, it is directly connected with the generator. In some situations, it is connected through gear system. That we will see later. So if the tip speed ratio is around 5, as far as this graph is considered, then you will get maximum power. There is a bets limit which is around 55 or 56%. That's what is somewhere there. So it is slightly less than that. Now, what is this? When the wind speed increases, then the electrical power that is coming out of the generator, wind power increases, the power that is coming out of the turbine also increases, and hence the power coming out of the generator also increases. So if you look at this, below certain speed, let's say 4 meter per second. Typically, the good wind speed means around 10 meter per second, 12 meter per second. That is a good wind speed. But if it is very less, like 4 meter per second, it is not going to be operated because it is not going to be economical. If the wind speed is very low, the power that we will be getting out of that system, overall system is going to be very less, so there is no use, it is not no use to operate it. But beyond 5 meter per second it is operated, and then the electrical power that is coming out of the system is also linearly increasing as the speed increases, right. But if you see at 15 meter per second, then it is 15 to 25 meter per second, it is constant. Okay, there are two questions here. Why it is not continuously increasing? Why it is like kind of a saturation, 15 to 25? But after 25, if you see, it is almost zero. Nothing is there. Graph is not there. I am converting this graph into sentences. From 5 meter per second to 15 meter per second, the electrical power that is coming out of this system is continuously increasing with wind speed. 15 to 25, it is constant. Why it is constant? Why we are not getting it? And after 25, zero. Anything you want to say? So I have to say, okay. We have installed a generator. Typically in that terrain, what is the speed? Based on that speed, we have chosen a generator of this much capacity. Let's say 100 kVA. We have installed. But suddenly in that same terrain, the speed is very high, which is capable of giving 120 kVA. What did I say? 100, right? 120, which is capable of giving 120. But we cannot change. We have already installed. Most of the time, the speed is such that whenever we have an electrical system or any other system also, if it is operated very close to full load, the efficiency is maximum. But if it is operated at under lesser loaded situation, then efficiency is coming down. Most of the time, the speed is such that it corresponds to 100 kVA. So we have installed the generator. But suddenly, sometimes the speed is very high. Instead of 12 meter per second, it's going to 15, 18 meter per second, which is capable of leading to higher power. But we have already put up a generator. We cannot change the generator. So therefore, that time we will have to adjust the turbine blade such that only we will get 100 kVA. Right? Although there is a possibility. But thinking 120 kVA if I put, then most of the time the power is such that less than 100 kVA, then the efficiency will be very less. So then that is not an optimum design. Somebody has to do a study in this terrain. What is the typical speed most of the time? So if I go for 100 kVA, what will be the return I will be getting? If I go for 120 kVA generator, what will be the return? If the return is less in terms of energy that is generated, then it is of no use. All right. But after 25 meter per second, the turbine that is made, that is unable to withstand that mechanical power that is coming out, right? Up from 15 to 25, it is to take care of the electrical integrity of the system. We have already installed the generator cannot give more than that. So therefore, we are doing that pitch angle control of the turbine blade such that the energy that is taken or energy that is converted from wind to mechanical to electrical, it is being optimized at that level. But after 25 meter per second, it is huge. Now whatever turbine we have installed, that cannot withstand that speed. Turbine in the sense, I am not talking about the tower, I am talking about the blade. Many places the blades are broken and they are thrown out actually. So therefore then the whole system is stalled. The whole system is stopped. Although we get huge electrical power, considering the mechanical integrity of the system, the complete plant is shut down. Is that clear? 15 to 25, we want to take care of the generator, otherwise the current in the windings of the machine will be huge, right? But beyond 25, we are completely shutting down, otherwise the blades and all will be broken. So that to take care of the entire system, sometimes whenever it comes, let's say it comes for a few minutes, so that time it has to be stopped completely. Something written, protecting the generator here, protecting the turbine beyond 25 meter per second. We have the lift. The lift is going at a slow speed, right? What is the speed? Approximately? 5? No, don't tell me kilometers per hour. I am not able to visualize. Can you tell me in terms of meter per second? 2 meter per second. Okay. 2 meter per second, slightly, मुझे लग रहा थोड़ा high speed. Okay. So 2 meter per second, let us say. But what is the motor that is connected for lifting this cabin? That is a high speed motor. So this is a low speed load. We are standing there, it is a low speed load because we are going at a very slow speed. But the machine that is connected is high speed motor. Why high speed motor is connected to a low speed load? So obviously there is an interface needed between systems which are operating at two different speeds. Motor is rotating at high speed, whereas this cabin is going at slow speed. So obviously it cannot be connected directly, right? There has to be an interface. What is that interface? Gear system, right? So similar to transformer that you have in electrical system, high voltage, low voltage, we have a transformer. The analogous thing in mechanical side is a gear system, right? So the gear system is in, so why don't we make a low speed motor and connect low speed load, because it's going very slowly. Why don't we connect directly low speed motor? Why are we going for high speed motor, and why are you introducing one more gear system? That is what I am saying now. Hanji? Yeah, if the speed is high, keep the left hand side, power is equal to torque into speed, okay. Keep the left hand side the same, because 3 or 4 persons are standing, so how much power is required? Let's say 20 kilowatt required. So left hand side is fixed power. Power is equal to torque multiplied by speed. Suppose if we go for a low speed motor, I want to get rid of the gear system. When you are eliminating mechanical system, the efficiency of the overall system improves. How it improves? Because the gear system, although we introduce, it's not like 100% efficient. So it is 95%, some 5% of mechanical transmission loss is gone. So again efficiency comes down, and again you are investing money on this gear system, and once again one more component has gone. So therefore the reliability, whenever there is a breakdown in the gear system, whenever there is a fault in the gear system, for replacing it, so during that time once again shut down, right? So the reliability of the overall system goes down by introducing additional components. So considering all this, why can't we eliminate the gear system? Why don't we directly connect this low speed motor to the low speed load, right? That's what I'm going to. Suppose in that case, power is equal to torque into omega. Certain things I'm not writing, is that it's okay, right? Torque into omega. So left hand side we have kept same. The moment the speed is less, in one case, if I say 2 meter per second, let's say it corresponds to 100 RPM, right? 100 revolutions per minute. So if I extend that into linear speed, let's say 1 meter per second or 2 meter. In another case, we go for a 1500 RPM motor, but we will put a gear, right? So then torque multiplied by speed is the power, right? If the speed is less, then that much power has to be taken care by the torque. So torque is high. If the speed is more, then the torque will be less. Okay. So in one situation torque is less, in another situation torque is more. Torque is equal to K phi I, right? Torque is a team effort between electricity and magnetism. If you have a current carrying conductor kept in a magnetic field, force is developed. Then radius multiplied by force is the torque. The moment if you say torque, high torque is needed, because I want to get rid of gear system, therefore I will have a high torque motor. Therefore flux density more or less same in all the electrical machines. The air gap flux density, all the machines, it's around 1 Tesla only, air gap flux density, because we have the iron core where the saturating value of flux density is 1.8 Tesla, but if you go and measure the flux density in the air gap, it is very close to half of that value, because the flux lines will not go straight, it will be diverging. So therefore the same amount of flux requires more cross-sectional area, therefore flux density will be half of the flux density in the core. So it's around 1 Tesla we will keep. So in all the machines, it is around 1 Tesla. Therefore torque is proportional to flux density and current. So now if you want high torque, then current has to be high, right? 100 RPM motor, 1500 RPM motor. Obviously with 100 RPM motor, the current has to be more. If the current has to be more, you have the slots tooth. I am talking about the stator. So then you have to inject more current in the conductors which are sitting in the slot. So if you have to inject more current, then the cross sectional area of the conductor has to be high. So therefore the slot volume should be high. So eventually the machine size is going to be big in size, right? If you go for 1500 RPM, for the same amount of power, left hand side 20 kilowatt, so therefore the torque will be less, and for the same 1 Tesla flux density, then the current will be less, so then the size of the machine will come down. So one important advantage of going for high speed system is the size of the machine will be less. There is an analogous thing in electronic side also. You have some systems for a low frequency, you have some system for high frequency. For example, 50 hertz transformer, if I say 500 kVA transformer 50 hertz, let's say this much volume, right? Suppose if I want to go for a 5 kilohertz same kVA, then the size will come down. Again 50 kilohertz, same. It's very simple. Inductive reactance is L into omega, right? So if you want this much inductive reactance, left hand side, in one case omega is 50 hertz, 50 into 2 pi. In another case it's a 5 kilohertz, 5000 multiplied by 2 pi. So then L value will come down, where inductance is N square mu A by L, number of turns square, permeability, area of cross section, and flux path length in the denominator. So obviously the inductor for 5 kilohertz, for the same amount of reactance or for the same amount of reactive power, it will be less compared to 50 hertz. So when you go for high frequency, the miniaturization happens. Similarly, when you go for high speed in mechanical, miniaturization happens. That is the first advantage. Second advantage is, when I say high torque machine, the current is high. Therefore, the heat that is produced by the machine is proportional to I square, right? So therefore, more heat is produced. High torque machine, 100 RPM means high torque, because left hand side we have fixed, same power, 20 kilowatt, right? Because 4 people have to be carried. So one case 100 RPM, so therefore it carries high current, the I square multiplied by time, that corresponds to the heat energy. In another case, less amount of current, so heat that is produced is less. So heat produced is more, heat produced is less. So heat ohmic loss in the conductor, in the winding, is more in high torque machine, therefore the efficiency of the system is less, right? And the third one is, since more heat is produced, somehow you have to dissipate the heat, otherwise that life of the machine will come down. So the high speed machine, less torque machine will live longer, because it produces lesser heat, therefore it is relatively cool. High speed machine relatively cool, therefore that machine will live longer. Am I going fast? Right. So these are the advantages of going for. Some fill in the blanks is also there. Whenever I give the fill in the blanks, most of the time first option will be the correct option. Most of the time, no? I don't know. For higher value of torque, machine size would be, what did I say? She doesn't trust me. Okay. So most of the time first option will be the correct option. Sometimes by mistake I would have changed. As a result, power density of the motor becomes low. Power density in the sense, this much volume available and I want to place the machine. Okay. In one case, let's say 5 HP machine I am placing, which is for a 1500 RPM. Now if I want to go for a 10,000 RPM, in the same volume I can place 10 HP, 15 HP. So then the power density of the second machine, which is operated at high speed, is higher. All right. That's what is written. Hence, high speed generator is coupled to low speed wind turbine through gear system. What I mean is, this windmill, you might have seen, what is the typical speed of the windmill? It's also written 20 RPM, 50 RPM, depending on the terrain. Okay. But if you look at the generator is high speed machine. So obviously 20 RPM windmill cannot be connected with the 1000 RPM generator. So interface is needed, gear. So that is the explanation I had given. Why we are going for, why don't we connect directly a 20 RPM generator? Then the interface can be removed. But for offshore projects in the sense the windmill installed in the sea, in the water. Okay. So there direct drive is preferred. Direct drive is without gear system. If this is a 50 RPM windmill, this is also designed for 50 RPM. The reason is there the efficiency, size, cost, all that are not considered. What is considered here is maintenance requirement. Suppose if there is a breakdown, how quickly you will attend to the problem. So there other things are not considered. Do you follow what I am saying? Right? So because going to the sea and then doing all the correct rectification, all that, it will take huge amount of time. So considering that requirement for offshore project, gear system is eliminated. Therefore, we have to go for a low speed generator. So the repetition. Okay. Now we will focus on the generator. What generator? Then we will go to the power electronic converter subsequently. If there is any question at any stage, you please interrupt. So there are AC machines only we are considering. Why can't we go for DC machines? DC machines are not preferred for most of the applications, mainly because of dash and dash. I don't know whether I can ask such questions because recording live, everything is going on, but I don't want to change the way of, little bit I changed because live is going on. DC machines are not preferred because of dash and dash. No, DC machines we can make. Based on some parts present in the DC machine, it is not preferred actually. No, commutator and brushes. Commutator and brushes. We have the winding here, and finally they are all terminated to the commutator. This is the commutator, and you will have the brushes. If you see the commutator, so you have some insulation. So this is a copper, and between two consecutive segments there is an insulation. Now brush is touching here. When this commutator is rotating, then there is a current interruption will be happening. Whenever there is a current interruption, you might have seen there will be a spark. Whenever you turn off some load, even fan, light, whenever you turn off, you might have seen some spark in that switchboard. So such machines, when you use in places like mines where there is a possibility of gas leakage, that small gas, little bit of gas and this spark, it will lead to fire explosion. So DC machines are not preferred for very harsh environment. That's one thing. Second thing, but here it is not an harsh environment. But here what is the problem is, with the time, the brush is sitting and the commutator is continuously rotating. So the brush will get eroded with the time. Although it looks like it is touching, but the effective resistance of the brush, contact resistance, is increasing. So whatever voltage is generated by the generator, some amount of voltage is getting dropped, and it is going to be a variable voltage drop. Initially it is less voltage drop, but gradually that voltage drop increases actually. And with the time, there is a possibility of oxide layer formation because of that arc. And this, so there will be oxide layer formation, it will be black in color. So once again, because of that also contact resistance increases. So effectively it's not going to be an efficient system. Periodically it has to be cleaned, or the brushes need to be replaced. So maintenance requirement is more with the DC machines. So if there is a possibility to get rid of DC machines, that is ideal. Okay. So AC machines, we have concluded AC machines. In AC machines, there are two machines. There are only two machines, synchronous and asynchronous. Synchronous means conventional synchronous machines, whatever second year, third year students might have studied. And other synchronous machines are this BLDC, permanent magnet synchronous machines, synchronous reluctance motor, switch reluctance motor. All these can be categorized. The only thing is stepper motor and switch reluctance machine. These two, we don't go for AC supply, we will go for DC, but otherwise all the other machines it is AC, including DC machine also. DC machine also externally you give DC, but the commutator converts the DC into AC. So all machines are AC machines except stepper motor and switch reluctance motor. But I humbly request you, don't write DC motor as AC motor. You write DC motor as a DC motor, but actually it is not DC motor. Okay. Synchronous generator, you are providing mechanical power to the rotor. So field winding is sitting in the rotor and the armature winding is sitting in the stator. Three-phase winding sitting in the stator and one single winding sitting in the rotor, to which you will give dash supply. Second year student? DC supply. Second year? Okay. You are? Oh, yes, in your second year, correct, okay. So I did not specify BTech or MTech, I said second year, okay, it's matching. You are a very obedient student. Okay, so I think you have not studied this synchronous machine. Very good, not an issue. There is nothing. Field winding and armature winding. Field winding is sitting in the rotor, armature winding is sitting in the stator. You can change also. But conventionally for big synchronous machines, field winding is sitting in the rotor, armature winding is sitting in the stator. In case of so-called DC machine, field winding is sitting in the stator. For that also you are not responding. Anyway, it's fine. That also you have not studied. DC machine you have not studied. Okay, no problem. So, okay. Then I will give some intro. Motor is a system which converts electrical to mechanical power. Generator is a system which converts mechanical power to electrical power. Constructionally, there is no difference. It's a machine. Whether it's a motor or a generator, how will you categorize? It's a machine I have kept in front of you. How will you categorize whether it is a motor or a generator? Depending on what power we are feeding. If we feed electrical power, then it is a motor. If we feed mechanical power, then it is a generator. Constructionally, there is no difference. And there is one field winding, one armature winding. Current carrying conductor placed in a magnetic field produces motoring action. And if a conductor is moved in a magnetic field, EMF is induced. If a conductor is moved in a magnetic field, EMF is induced. If a current carrying conductor is kept in a magnetic field, force is produced. So constructionally there is no difference, same machine. Okay. So since we are talking about generator, we are feeding mechanical power. So in this wind energy conversion system, who is feeding mechanical power? Wind and then turbine. You can say turbine. Turbine is converting wind power to mechanical power. Mechanical power is converted into electrical power by generator. So turbine is providing the mechanical power. So that shaft of the turbine is connected to the shaft of the generator through gear system in one case, and in another case gear system is not there. And field is either it could be electromagnet or permanent. Electromagnet means what? I have a core over which I have a coil. Now that coil is given a battery DC supply. So then one side it is a north and another side is south. So we have created a magnet. So that's called electromagnet. By creating a magnet with the help of electrical excitation, it's called electromagnet. Some situations I don't want to have the winding, because whenever you have the winding, I square R losses will be there, ohmic loss. Typically we call it as a copper loss, but you can avoid copper loss. The reason is if the conductor is made up of aluminum, you cannot call aluminum loss, but you have to call again copper loss, then it is not logical. So it is better to call as a ohmic loss in the winding. If you want to eliminate that ohmic loss, go for permanent magnet. But there is a disadvantage of going for permanent magnet. What is the disadvantage? If I want to change the intensity of the magnetic field, by changing the current, I can change the intensity of the magnetic field in electromagnet, whereas with the permanent magnet, if you have chosen whatever field is coming, you have to accept it. So there is a disadvantage. Okay. Now I will have to explain this. Since you have not studied machines, I will have to explain these two machines. Earlier I said in the previous session, but I will repeat it. It is something like a child is moving the magnet and keeping the iron pieces there, right? So EMF is induced depending on the relative speed of this iron pieces kept on the top of the paper, and the child is moving the magnet. So because of the relative speed, there is some EMF is induced, and if you provide a closed path, then current starts flowing, and that will result in one magnetic field. Then these two magnetic fields interact. Cross product between these two magnetic fields result in force or torque. In another case, instead of keeping iron pieces, you keep a magnet pole of opposite polarity. Let's say I am keeping north pole is facing like this, then keep a magnet, south pole is facing downward. So then north pole of this magnet, south pole of this magnet gets locked, and wherever it goes, this is going. So that is a synchronous machine. Okay. So synchronous machine, two magnetic fields are produced externally by us. Whereas in asynchronous machine, once again two magnetic fields, but only one magnetic field is given by us, another magnetic field is induced because of that's why it's called induction machine. Rather than induction machine, I prefer asynchronous. Why? I will tell you later. Okay. Now I will bring motor and generator together, not to confuse you, because motor is very much familiar. So I will start with motor and then switch over. In case if I make any mistake while talking, Anshul and Yogesh will correct me. Sometimes if I tell, so you have to carefully observe. Okay. Asynchronous. If I assume that whatever I keep iron pieces on the top, if I assume that that is also going at the same speed as the speed of the magnetic field, if I assume, then the relative speed between that iron pieces and that magnetic field is 0. If the relative speed is 0, then there is no EMF induced. Okay? EMF is induced if there is a relative speed, right? No EMF and there is no current, therefore no magnetic field and hence no torque, no rotation. So therefore, this will never go at the same speed as that of the magnetic field moved by the child. That child moving the magnetic field, which I have explained as a traveling magnetic field, revolving magnetic field, rotating magnetic. In all books it's read as revolving and rotating, but I request you to use the word traveling magnetic field so as to take care of the application of magnetically levitated train. So there you cannot use the word rotating magnetic field. That is not logical at all because there is no rotation. But if you use the word traveling magnetic field, it is taking care of linear machine as well as the rotating machines, because that linear machine is a very big application. Whereas in case of synchronous machine, both are going at the same speed. Whatever is the speed of the magnetic field, the same way other rotor is also going at the same speed. So there is a synchronism. So if I talk about a motor, synchronous motor is one wherein stable torque is produced only at synchronous speed. What is synchronous speed? Speed at which the magnetic field is moved. And if you look at the expression, it will be 120 F by P. So this is a connection between mechanical speed and electrical speed. Mechanical speed and electrical speed, how it is related? Electrical speed is equal to dash multiplied by mechanical speed. No, she's doing like this. No, I am asking a question. Electrical speed, correct. Pole pair. That I had explained, right? Suppose if you have a north pole, south pole, if I make one rotation, and if I see the waveform EMF induced in this winding, if I capture and see in the oscilloscope, one positive, one negative will be there, right? So when I complete 360-degree mechanical rotation, I am seeing one cycle in the oscilloscope. So that is also 360-degree. Whenever you see waveforms, voltage or current, we can say electrical, right? So this is a 360-degree. 360-degree mechanical rotation corresponds to 360-degree here. Now if I have a 4-pole, north pole, south pole, north pole, south pole. When I rotate the conductor here, and if I capture the waveform EMF induced in this winding and see it in the oscilloscope, when it crosses north pole, let's say positive. When it crosses south pole, negative. When it is again crossing north pole, positive. South pole. So I will have 2 cycles of waveform. 2 cycles of waveform means 720 degree. 720 electrical degree is produced because of 360-degree mechanical rotation, right? Therefore, electrical degree is equal to pole pair. 4 by 2 multiplied by mechanical degree. 4 by 2 means 2 multiplied by 360, 720. Suppose if I talk about a two-wheeler, electric two-wheeler, there is approximately 40 poles. 40 poles means what? Because the speed is very less. Speed, if you see, the speed and poles are inversely proportional. If you want 1500 RPM, you will go for 4, considering a 50 Hz supply. If you want, let's say 300 RPM, what is this number of poles? Okay, no, she is giving hint for you people to think. She knows the answer, 20 I think. Oh, okay. If I want to get a 300 here, 300, what should be the number I asked? The numerator is 6000. 6000 divided by 20, that's what she said, because 0 is not having any value, right? So that's why she said 2. Correct, no? 3000, okay. I did not say it properly, my problem actually. So poles and speed are inversely proportional. So in the two-wheeler, the speed is around 300 and 400 RPM, right? So therefore the poles are very high, 40 poles. 40 poles means what? North pole, south pole, north pole, south pole, north pole, south pole, and so on. Do you understand what I mean? 360 degree, north pole, south pole, north pole. So that means what? This north pole, this south pole, this distance is how much? What is this distance? 360 degree. 360 degree. One north pole means 180 degree, south pole means 180 degree. So 360 degree. I will never talk about mechanical degree. Because I am from electrical, I will speak about electrical only. This north pole, this south pole, this corresponds to 360. Do you understand what I am saying? Right? Yeah, one north pole means 180 degree. Right? Anyhow, we are deviating. What is this ns? Ns is the speed at which the magnetic field is going. Okay? Speed at which the magnetic field. So F is the frequency of the signal, frequency of the supply, and P is the number of poles that the machine is designed for. how the machine is designed, by having the conductors being distributed in the circumference, it is possible to create any number of poles. Okay. If I talk about the ceiling fan, the speed is around 350, 400 RPM. So the number of poles around 12 and 14. Okay. So in the entire circumference, the conductors will be wound like this. Should I show? Anshul, okay, no? No. Are you disturbed the way I am doing, or? Okay. So this is about the ceiling fan. If you see this one, the conductors are hundreds of turns are there. So it is done like this. And subsequently this one, it will be counterclockwise. Then this one will be clockwise, counterclockwise, and so on. So now if I see the center of this one, so when the current is flowing like this, right? When the current is flowing like this, right? So then the flux will be going this way. Now when the current is flowing like this, then flux will be. So then flux goes this way and comes this way. I am just talking about the external winding. Flux goes like this, flux comes out like this. So then this, if I consider convention, this is a north pole, center. This is a south pole. So north pole, south pole, north pole, south pole, north pole, south pole. It may be 12 or 14, right? To match with our speed. We are comfortable with 300, 400 RPM. We don't want 1500 RPM. If it is a 1500 RPM, then we will have such 4, only this 4. But when it is rotating at 1500 RPM, we are not comfortable. Even with the 350 sometimes, we are not comfortable. Paper is all flying and so much noise is also produced, all that, right? So the spacing between this, center of north pole, center of south pole, what is this spacing? 180 degree. So I will not talk about mechanical, I will talk about electrical. 180 degree, when I say it's electrical, right? So basically it is a two-phase machine, because to our home we don't get three-phase supply. So to produce a traveling magnetic field, the minimum requirement is two-phase supply should be given to two-phase winding, two-phase. Two windings should be there, and those two windings, the magnetic axis of those two coils should be displaced in space by 90 electrical degrees. See, only from three-phase onwards, it is a 360 divided by number of phases. But for two-phase, it is not 360 by 2. There is an exception. Two-phase means 90 degree. Okay, there is an exception, because if you make 180 degree, the effect produced by these two windings will cancel out each other. So it is not a two-phase. Two-phase means 90 degree. So you should not apply 360 by 2. Two-phase means 90 degree. So what we do, the magnetic axis for this coil, the magnetic axis is this one. And for this coil, the magnetic axis is this one. Already we have said that this is a 180 degree. Therefore, the spacing between this center and this center, 90 degree. So we have made a machine wherein the magnetic axis of the two coils are displaced in space by 90 electrical degrees. 90 electrical degrees. Now to this, we have to give a two-phase supply. But to our home, we don't get two-phase supply. We get, so this is what I said, the coils made. So we get a single phase supply only, right? Two-phase supply means what? You should have either two voltage signal or two current signals displaced in phase by 90 degree. If you see in the oscilloscope, two signals should be there. So what we are doing, we take two windings. These two windings I have shown. Two coils, and we are giving a supply, and you draw the phasor diagram. Since these two coils are not located at the same location, one is a inner circle and outer circle. Obviously, the resistance and inductance of these two coils will be different. Therefore, current IA, IB are like this, right? Now we make use of the property of passive elements. I want to have the shift between these two currents 90 degree, right? So what we do, one of these coils, you can add capacitor to any of these coils. I keep on changing the capacitor. So then this capacitance effect and the inductive reactance both cancel out at one point. Then voltage and current are in phase. Then you keep adding capacitance. So then that branch is becoming capacitive in nature. The current is leading the voltage. So at one stage, when these two currents are 90 degree, angle between these two currents is 90 degree, stop. So that is it. So now we can add the capacitor to either to coil A or coil B, right? Which is optimum one. So now IA, so I want to shift, let's say this is a 40 degree and this angle is 20 degree, right? Now you want to make 90 degree. So this 20 degree means this IA should be somewhere here 70 degree. Suppose if I have decided to make this, if this is a 40 degree and if it has to make total 90 degree, then you have to put a large value of capacitance. Once again that cost will be on the customer. So it is not an optimum design. So if whichever current is very close to the voltage, to that winding you add the capacitor. Sometimes no, I get deviated, you will have to guide me. So where did I stop? Ns is equal to 120 F by P. The number of poles is decided by what speed you want actually. For a two-wheeler and for fan and all, it is a low speed machine. Sometimes no, this fan also they sell high speed fan. What they do? High speed fan. It is generally higher in price, right? Approximately what is the price difference? I don't know. Maybe you can tell me. Approximately high speed fan compared to the ordinary fan. What may be the price difference? 1,000 rupees? Okay. What they do? They reduce the number of poles. Basically, they reduce the copper and then they sell it at higher price. Okay. So if it is not sold at higher price, you will not buy it. Okay, you will say no, this may not be the proper machine, something like that. So they will reduce the number of poles and you can make it 2 poles also, then it will be 3000 RPM, very high speed actually. But instead of 12 or 14 poles, they will go for 8 poles, 10 poles, something like that. There is no other technology involved in that, it is very simple, right. So now both these machines, the magnetic field is taken care by a DC supply, but the speed of the magnetic field is decided by dash. Speed of the magnetic field. Okay. No. Now I am going to generator, and generator of this wind energy conversion system. Okay. Sometimes I do like this, not to confuse you. Quickly come to the point actually. The field winding is sitting in the rotor, and we are giving a DC supply. So north pole, south pole has come. Okay. Now that rotor is being rotated by turbine. I will skip that gear system, directly turbine. So therefore, the speed of the magnetic field is decided by the turbine. Now you have the armature winding sitting in the stator. So if it is going slowly, the frequency of EMF induced will be less. Okay. So north pole, south pole, conductors are stationary, north pole, south pole. Right. Now whatever EMF is induced, that is what we are going to tap and feed it to the grid. With appropriate frequency conversion we will do later subsequently with the help of our electronic converter. Now the conductor is sitting, north pole, south pole is rotating, right, and whatever EMF is induced that you can see in the oscilloscope. Now next one, it is rotating faster. Why it is rotating faster? Because that time the wind profile is better, the wind speed is good, therefore turbine rotates faster and hence the rotor is rotating fast. So then the rotor you have north pole, south pole. I am just taking a 2 pole. So therefore the frequency of this changes. So basically the frequency of the EMF induced in the stator winding depends on the wind speed and it is continuously changing depending on the wind speed at that time. Right. So in one case, there is a difference between the speed of the rotor. Now I will go to motor now. There is a difference between the speed of the rotor and speed of the magnetic field. In another case, both rotor and the magnetic field go at the same speed. That is a synchronous, asynchronous. Okay. In case of asynchronous generator, okay, I will tell about asynchronous motor. Synchronous motor, I said it is a motor which produces stable torque only at synchronous speed. Whenever I say synchronous speed, it is the speed of the magnetic field. It is not just a random number, it is the speed of the magnetic field. It produces stable torque only at speed of the magnetic field. Asynchronous machine in the sense, asynchronous motor, I am talking about motor now, it produces stable torque. I want you to make an analogous statement. Synchronous motor, it produces stable torque only at synchronous speed. Now I am doing English test. Asynchronous motor means it produces stable torque. Great man. At any speed other than synchronous. At any speed. Okay. When I say any speed, if it is a 4-pole machine, magnetic field speed is 120 multiplied by 50 divided by 4, which is 1500 RPM. Okay. In first case, the rotor will go at 1500 RPM because it is synchronous. Second case, the rotor speed will be other than 1500, very good. Now range we can do, less than 1500, more than 1500, equal to, Anji, now I have given 3 options. Isko jodo, generation chodo, even for a motor, what is the speed of the rotor? Less than synchronous speed, greater than synchronous speed, other than synchronous. 3 options I am giving. Okay, most of the time I said option A, but here there may be change. Tell me. Less than. But this is not matching with this gentleman already given one answer, other than synchronous speed. That's what you gave. But now you are choosing C or B? I asked him. Oh, you are choosing B. Okay. He is choosing B. What about you? Current knowledge.
Because right now you said that other than synchronous speed, it will work on other speeds. So that's why I will choose C.
You are choosing C. Okay, you are. I have not chosen B. I am giving 3 options and I am asking you to give the option. That gentleman gave option B, and earlier you made option C, but many people are opting option B. If you want to change, you can change. But if you want to stay back with C, you can say. What about you? Option A. C, okay. C. Okay, because you did not study, right? It's better you have not studied. So we will see. C, we will see. Okay. AC machines we have concluded. We will go for AC machines. When AC machines means synchronous machine, this is the first one, synchronous generator. And then induction machine, there are 2 categories. One is a squirrel gauge squirrel gauge rotor, and another one is a phase wound rotor. Squirrel gauge rotor in the sense you don't have any winding in the rotor. Those who have not studied, just leave. There are 2 classes of rotor, that's all. Those who have not studied, just listen, it's okay. Squirrel gauge rotor means there is no winding in the rotor. You have solid copper conductor or aluminum conductor in the rotor. And phase wound induction machine means once again you have 3-phase winding in the rotor, like similar to that of stator winding. If stator is made for 4 poles, rotor winding is also made for 4 poles. There is a match between the stator construction and the rotor construction. Okay. So for that asynchronous machine, 3 topology are there. These 2 are for squirrel gauge machine, wherein you don't have any winding in the rotor, whereas here you have a winding. And this is a synchronous machine. Okay. Now this is a representation of a transformer and then grid. If you are using squirrel gauge induction machine, it is directly connected to the grid. Okay. In another one, there is a difference between these 2. For this I have to draw the characteristics. I will do subsequently. I hope I have, otherwise I will draw. In another situation, you want to go for a variable speed. I will explain what is the use of this. When it is possible to connect the stator windings directly to the grid, why are we going for this power electronic converter? Because these power electronic converters, although in this picture it's shown small, but it's all going to be very big, because typically the rating of a windmill, typically around 10 megawatt. 10 megawatt in the sense for your campus power requirement may be dash megawatt. Please fill up the blank. Maybe MTech, PhD students can, for your campus, I don't know. Since I don't know, you can tell any number. For your campus, power requirement may be hello, 0.5 megawatt. Okay, that is the guess by IIT Gandhinagar. IIT Gandhinagar students are giving less power to you. Okay, 0.5 megawatt is somewhat less for such a big campus. It's a 400-acre campus, right? 600? 320. Okay, so you are giving a right number. Okay, but I don't know, whatever number you can say. So 0.5 megawatt is somewhat less. 2.25 megawatt. Is generous in giving that much power. No power, they will waste it unnecessarily. We should not give less also. We should not give too much also. So it should be optimum, right? So 1.5 megawatt, I think it's enough, adequate, more than enough. So if I say 10 megawatt, so that means what? it can, one windmill, suppose if full power is coming out of that windmill, if that wind power, Vayu Bhagavan is also with full intensity, so that can meet the requirement of 7-8 such campuses, one windmill, alright. So obviously all these transistors which are sitting in this rectangular box, it's all going to carry thousands of amperes, okay, and also it's not going to be a single device, many devices are going to be connected in series and parallel in order to meet voltage and current rating, right. So when it is possible to exclude the semiconductor devices, directly you can connect the grid and it is possible, why are we going for it? Obviously there must be some advantage, this I can explain with the help of characteristics if I have, otherwise I will draw. In another case, you want to feed field supply to the rotor winding. Is this understood? You want to give a DC supply to the field winding sitting in the rotor, right? Is this diagram legible for the last row people? Okay. Field winding is energized by a DC supply. Motor or a generator, we have to provide field, right? And whatever active power coming from the stator, so that has to be fed to the grid, but the frequency of the supply that is coming out of this stator winding depends on wind speed. Obviously you can't directly connect to the grid, so you have to put a frequency converter. What is frequency converter? Which converts AC to DC, DC to AC. This side it could be 40 Hz, this could be 50 Hz. You can call two converters connected back to back, but I use the word frequency converter so that clarity is there. Why are you introducing that interface actually? So in this case again you are putting a frequency converter here. So this I will have to explain. So this three windings which is sitting in the stator, whatever supply coming directly fed to the grid with the help of transformer, and then rotor is also we are providing power or we are taking the power. So this I will explain. So right now some of the things may not be understood by students who don't have any exposure to machines, but it's okay. I will try my best to fill up. Okay, the first one, squirrel gauge rotor. Squirrel gauge rotor we have, and we cannot access the rotor, and the stator is directly connected to the grid. So this is the torque speed characteristic. Actually I am doing for a motor first. For a generator you have to do the mirror image, so it will be drawn like this, okay. So operating point is somewhat is going to be here. Actually this portion is of no use actually. So only this line is enough, more than enough. Operating point is going to be somewhere here. You might have seen in the lab, if it is a 4-pole machine, the no load speed is around 1490 rpm, and for the full load speed it is 1440 rpm. So it is somewhere here only. So all this, the entire portion is nowhere required, okay. So it is somewhere here, operating point, full load. So this, the difference between this point and this point is, this is typically 1/3 of this maximum torque point. This is typically 1/3 of that. So this is the full load. Now if I talk about a generator, the same line you extend here, operating point is somewhere here, okay. So the torque is negative. If the torque is positive means, if I am saying a motor, torque negative means it's a generator. So this much torque and whatever is the speed, 1440 rpm. So that torque multiplied by 2 pi multiplied by 1450 rpm divided by 60, 2 pi n by 60, that is what is going to be the angular speed multiplied by whatever is the torque. So that is what is going to be the output mechanical power in case of motor. Similarly for a generator, if this is the torque, this much torque multiplied by that speed, the speed will be above this point, right. So then that torque multiplied by the speed, that is what is going to be the generated power, we can say. If it is connected to the grid and if it is a 4-pole machine, then the magnetic field will always go at 1500 rpm. Is that understood? If it is a 4-pole machine connected to the grid, 50 Hz supply, the magnetic field will always go at 1500 rpm. The speed difference between the rotor and the magnetic field, it will be very small number, very small number. In case of motor, it is a positive slip. Positive slips in this, let's talk about 1450 rpm, 50 rpm difference. Slip is ns minus n divided by ns, right? Numerator 1500 minus 1450 divided by 1500. So 50 divided by 1500 into 100, how much it is? Okay, 3%, 3% slip. But if it has to be a generator, but operating point should be somewhere here. Okay. So once again it is a 50 rpm plus. Magnetic field will go at 1500 rpm. The rotor has to be rotated at 1550 rpm. So then the numerator will be again minus 50 divided by 1500. Okay. So it is a minus 3% slip. Agreed? If the stator is permanently connected to the grid, then and if the rotor is rotated between a speed, not understood. Okay. I have a machine here. First I will talk about motor. The shaft of the machine, if I am not connecting any load, and you see, no, seeing like this, there is a machine, okay? Everybody is agreeing that there is a machine. Hey, why you are feeling shy now? So there is a machine here, shaft of the machine. I am not connecting any load. What may be the speed of the machine? High speed or low speed? I think he is ambassador for all. There is a machine, shaft is there, I am not adding any load. If there is no load, whether it will rotate fast or it will rotate slowly, if there is no load. See, you are running, you are not having shoulder bag. In another case, you are having a shoulder bag. In which case you will run faster? Without bag, right? So similarly, load is not connected, so it will rotate faster. So that point is somewhere here. Now I am adding some load. What will happen? Speed decrease. What will happen to the torque produced by the machine? When I am adding load, what will happen to the torque? Torque has to increase. And the purpose of adding the load was to convert more electrical power into more mechanical power. Suppose if that machine is not producing more torque, it's not a motor at all. Right? The purpose of adding the load is it has to produce more torque, but since we are loading, then the speed will drop, torque will increase. So that point is going somewhere here. Initially it was here, then it is going somewhere here. And if I keep on adding load, it will. So that's all the characteristics of induction motor. It is going to be somewhere here only. There is no point in adding all this because we are always operating here only. When the motor is not loaded, the speed is very close to 1500 rpm. 1490 rpm I said. When the motor is loaded, the speed drops, torque increases. Alright? This is a motor. Now generator is like a mirror image. When I say mirror image, don't draw like this. I am going this point. Okay? If the rotor is rotated at a speed, see, initially magnetic field is going and the rotor is moving at a speed less than that. Suppose if the rotor is moved, in our situation rotor is moved compared to the magnetic field, therefore power is getting transferred from rotor to stator. In case of motor, you are giving a three-phase supply to the stator and you are establishing a magnetic field, right? So now the rotor will move at a speed less than the speed of the magnetic field. The power conversion is from stator to rotor. Suppose if you reverse and if you provide a mechanical power, such power transferred to rotor to stator, in the sense mechanical power is converted into electrical power. Okay. So if I want to get full capability of the machine, if I want to use, then for a motor, the operating point is somewhere here. I will not go beyond that, right? So then that means you are overloading the machine, which is not appropriate. If you want to get full capacity, let's say this is the torque point. Similarly, if you want to have full capability as a generator, whatever is the torque, negative torque. All right. If I say this is a 1450 rpm and this one is a 1550 rpm. Agreed? Now slip is ns minus n by ns. In one case it is a 1500 minus 1450. Whatever I am writing now it's for a motor. In another case it is a 1550. 1500 minus 1550. 1500. So this is slip is 0 and this is 1 and this side it is going to be a negative slip. If I am making any mistake, no, please correct me. Okay. So this side positive slip, this side negative slip. The operating point 1450, 60, 70, 80, 90 depends on motor, depends on load. Great. Similarly, if the rotor is going at 1550 rpm, I will get maximum electrical power out of generator. But it could be 1550, it could be 1510, 1520, 1530. That speed depends on I will repeat my question properly. I am not asking properly. So what the speed of the rotor 1510, 1520, 1530, 1540, 1550 depends on generator speed, but generator speed depends on mechanical. So it depends on wind speed finally, turbine, right? So if you are getting a higher wind speed, then the turbine speed is more. Then it is coming, so then this much torque is the counter torque. I will not use torque developed by the machine. Torque developed by the machine when I will use if it's acting as a motor. Right now it's an opposing torque, counter torque. Because the turbine is giving a torque, this generator windings produce a torque which is opposing. As long as there is an opposition, then only there is a power conversion from one form to another form. See, when I am saying something, if you simply agree, no conversion, right? If you are opposing, like he said, no, kuch bhi samajh mein nahi aa raha, right? So then only I have to try my best to explain. But if he is not opposing me, no conversion, right? Same thing. Whenever there is, so this is called counter torque. So counter torque will be more if the turbine speed is more. That depends on wind speed. Okay. So now, can you tell me the speed range of the induction motor? Speed range of the induction motor just to 50 rpm. No load, it is a 10 rpm difference. Speed difference between the magnetic field and the speed of the rotor. 1490 rpm. No load situation when load is not connected. When the full load is connected, full load in the sense that time the current in the stator winding is a rated current. If it is designed for 5 ampere, it will be 5 ampere. You should not load it beyond. Although you can keep on loading the shaft, but the windings will be carrying 5 ampere, 6 ampere, 7 ampere, but it is designed for 5 ampere. But if you are injecting more current for a longer duration, that the insulation over the winding that will be stressed and there will be a damage. So you should not do it. All right. So the speed range is just 50 rpm. 1490 to 1450, 40 rpm. The same way it is applicable here also, only 50 rpm. So it is called the narrow speed range induction generator. What it means is, if the wind speed is such that the turbine speed after the gear, if the speed is between 1500 and 1550 rpm, then only you will have the generation. Whether that is understood? Right? Suppose if I say 1500 rpm corresponds to 10 meter per second wind, 1550 corresponds to 12 meter per second, let's say 10. So if the wind speed is between 10 and 12 meter per second, then only you will have the generation. So it is like a narrow speed range induction generator, so which is not looking like a logical, right? You cannot give instruction to wind that all the time you have to be like this, because I have installed squirrel gauge induction machine, which is a nice machine. There is no winding in the rotor, and you need not have slip rings and brushes, maintenance requirement, everything has come down. Please serve the humanities. Okay. So like that we cannot tell wind. So obviously it is not looking logical. So suppose if the wind speed is such that 800 rpm is the speed of the rotor, 800 rpm, this is rejected. So what we can do? But I want a characteristic like this. Okay. Now, this induction motor is installed in the electric train. Electric train, whatever we have, induction motor. You are going at 100 kilometers per hour, Shatabdi train, let's say 120 kilometers per hour. That's what 1450 rpm. Now, we are approaching the station. So the speed has to be reduced to 60 kilometers per hour, 40 kilometers per hour. What I should do? Reduce the synchronous speed. Great. Because the speed of the rotor is less than the speed of the magnetic field. Reduce the speed of the magnetic field. 120 F by P. Now we have three things. 120 we have, F we have, P we have. What you will change? F. Very good. Okay. One student in IIT Gandhinagar said, why don't we change 120? Okay. I never thought about it actually. F को क्यों change कर रहे हैं? 120 को change करो. Then I was thinking how this 120 has come. P by 2. 1, 2 has come because of that. So 120 is 2 into 60. 2 has come from poles. And the 60 has come from what? We are converting revolutions per minute, revolutions per second. So the connection, 1 minute is equal to 60 seconds. So finally he wants to change the rotation speed of the earth and so on. So that no, this minute and second, that 60 can be changed. He wants to change the world, rotation, universe, something like that. I gave up, no. I mean, I never thought about it. I was ekdam dull candidate during college time. Whatever sir says, teacher says, madam says, I accept and do and get marks. But our students know, ekdam, I want to change 120. Fortunately, another student was telling, so why don't we change the division operation? Why don't we put integration, differentiation instead of division? So it's very difficult to address these queries. Okay, where did I stop? Reduce the frequency. If I reduce the frequency, motor. First we will talk about motor. What will happen to the characteristic? Like this. For 50 hertz supply, if this is the characteristic, for 40 hertz, 30 hertz, 20, 10 and so on. So, but just by changing the frequency of the supply that is coming out of the power electronic converter which is fed to the induction motor, you can shift the characteristics. So once again the slip, if you see, suppose if the frequency is around 15 hertz and this is what is going to be the speed of the magnetic field and this is what is going to be the speed of the rotor. So if I see the difference, once again it will be 40-50 rpm difference. 50 rpm divided by this one you have to put to find out the slip. So again it will be 3%, 4%, right? Slip is very important. There should not be too much slip. Slip means what? Suppose if you put what is that, banana? So if you put that, you will slip, no? So that is what is the slip. So the slip should not be too much. If the slip is less, it is an efficient motor. I will explain you that later, right? So by changing the frequency of supply, you are able to cover dash. By changing the frequency of supply, you are able to shift the characteristic. See, we have made a motor, the characteristic is this one only. And this, such a characteristic was not possible. Such a characteristic was not possible before, before our independence. Why? No, before our independence, it was not possible to change the characteristic. Why? First transistor was invented in the year 1947. Okay. Okay. So before our independence, it was not possible. After our independence only, there are a lot of technological advancements. Don't ask me who invented transistor. That is not important. You get a feel, no? Jai Hind, no? So, just by changing the frequency of supply, you are able to shift the characteristic anywhere, right? So earlier, the only motor that was used for DC series motor. DC series motor, you will have the characteristic like this, rectangular hyperbola character. I am not drawing that. So rectangular hyperbola characteristics, wide speed range. With a single voltage, you are able to cover the entire speed range. Whereas with the induction motor, giving one frequency supply, you will always operate here only. If this corresponds to 50 kilometers per hour, it will be between 45 and 50 only. That's all. You cannot think of going at 20 kilometers per hour with the induction motor energized by a fixed frequency supply. Therefore, earlier the only motor that was used for vehicle application was DC series motor. But now any motor you can use because of power electronics. Okay, power electronic converters. Any motor you can use. You just choose the best motor that you think, and you introduce a power electronic converter. This is about the motor. Now I want to come to the generator. Just you have to stretch these characteristics. So when I say instead of 1550 rpm, suppose if it is 800 rpm, That means somewhere here, right? So, but the requirement is the speed of the rotor should be greater than the speed of the magnetic field, because we want the power flow to happen from rotor to stator. So then the speed of the magnetic field should be here. Then the speed of the magnetic field should be here in the sense it cannot be directly connected to the grid, because grid frequency is 50 hertz, 120 f by p, it's always 1500 rpm, it is fixed. So therefore there you will have to put power electronic converter. Now I will go back to that presentation, probably you will be able to understand. Although I have shown for motor, just you will have to stretch the characteristic, it's very simple. Now this side is always 50 hertz, but I want to have here 20 hertz. Do you follow what I am saying? Here it is a 50 hertz, but now since the speed of the wind speed and the turbine gear system, after that, since the speed is around 800 rpm, obviously I cannot directly connect to this. If I go for this, then the speed range is only this much, 50 rpm difference only, right? So that means we are instructing wind speed all the time, you have to be like this. So it is ruled out. What I am saying, very narrow speed range. Whereas here, anywhere you can operate. Okay, what is that we are paying for it? We have to introduce this frequency converter. So this is a power system operating at one frequency, constant frequency, and this is also kind of a power system operating at variable frequency, which is decided by the wind, right? So you have to put a frequency converter. So 20 hertz is here, convert DC, DC is converted to 50 hertz, right? Or you see this way also. Now there are two things. We are interested in generator and we are connecting the grid. Somewhere I am saying that convert 50 hertz into DC, DC into 20 hertz. So I am confusing. We want a power, right? We want power from year to year, but we are connecting this. Some doubts you have, right? So there are two powers, active power and reactive power, okay? Reactive power support is taken care by the grid. Reactive power means some magnetic field is to be established. So for motor or generator, I will make two statements which I made earlier. Motor means what? If a current carrying conductor is kept in a magnetic field, okay, force is produced, right? That force is ILB. If a conductor is moved in a magnetic field, EMF is induced. So if you see both the statements, what is common? Magnetic field. Magnetic field is to be established first, right? For this asynchronous machine or induction machine, depending on the speed of the magnetic field, the rotor will go at a speed slightly less than the speed of the magnetic field. For a generator, if the rotor is moved at a speed greater than the speed of the magnetic field, EMF is induced. So magnetic field is to be established. Magnetic field is established in the sense it is a current through inductor. Forget about capacitor, although that also corresponds to reactive power, but capacitor we are not going to discuss. So if there is a current through inductor, then that is called reactive power support, right? So that magnetic field is established by this grid supply, but whereas active power will be flowing unidirectional from this point to this point, okay? How do you understand that? If I capture voltage waveform and current waveform and see it in the oscilloscope, at this point, grid point, if both are in phase, that means what? Active power, active power. V is like this, current is in phase. That means active power is going from this point to this point. That is a convention. But if active power is coming from this point to this point, what will be the change in these waveforms? One waveform, so this is the voltage and this is the current, right? So this is V and this is I. I was about to show that grid connected, but I have changed the screen. So this is a white space in development, some more developments. Two screens should come. That also should come, this also should come. Please take this work in future. Okay. So what I am saying is, let's say this is the convention at the grid, V and I. So then the power is flowing from grid to the machine. But now I am saying active power should come from machine to the grid. What will be the change in these waveforms? Great, man. So this current will be reverse. This current waveform will be like this, right? So if I multiply Vm sin omega t into Im sin omega t, so all the time it will be like this. This is the reference, it will be like this. But if this is a 180-degree shift, then it will be like this. But it is a unidirectional power flowing from grid to the machine. Understood? This is grid to machine, and if this is 180-degree shift, machine to grid. See, I know I'm checking whether you people are alert or not. Okay. So machine to grid. All right. Okay. But in our case, this will not be the case. This is not going to happen, and even 180-degree shift will not happen. Why? Great, man. You're awesome. You're in second year? Third year. Okay. Awesome. If this waveform is shifted by 90 degree, let's say exactly 90 degree, what is meant by that? Only reactive power. There is no concept of active power. But in our case, reactive power support is needed, active power is needed. Active power means 180-degree shift, and reactive power means some shift will be there, right? So then finally, by doing this shift between the voltage and current waveforms, it is possible to control the active power and reactive power. I can speak like this, but I cannot show the simulation the way some masters are showing. I will talk like this. That's all my limit. Okay? Okay, no. No. I have not tried, so I cannot show. I can do show off up to this point only. Beyond that, he will take care, right? So just by adjusting this angle between voltage and current waveforms, you will be able to decide how much active power will be flowing, how much reactive power can be supported. Okay? I will not use the word how much reactive power flow. Why? I will have to show. Earlier I said in space I was explaining the expressions, but now I thought I will have to show this. If there is a purely resistive load, then the waveform will be like this, right? There is a bulb, but power waveform. So that means what? Effectively the power is transferred from this location to the bulb, and it is converted into light energy. So this is about pure resistance. Suppose if I go for inductance, where is the current is lagging the voltage waveform by 90 degree, right? And if I say voltage is sin omega t, current is sin omega t minus pi by 2, right? So then if I go for product, sin omega t cos omega t, which is like a sin 2 omega t, so that means it will be like this. So if it is like this means what? If I have a pure inductor and if I have a supply, sinusoidal voltage supply, then if I say negative, positive, power is coming from the source to inductor. Negative means power is going from the inductor to source. Actually, power is oscillating back and forth between the source and the inductor. Okay, I will not say source and the load, because for me, this inductor doesn't look like a load. Sometimes it takes it and some other time it gives it. So I cannot use the word load. It doesn't look like logical. So reactive power is being, most of the books it's written reactive power is absorbed by the inductor. For a capacitor, if you put the same waveform will be like this, right? For capacitor, it gives reactive power, inductor is absorbing the reactive power. It is like projecting inductor as inferior compared to capacitor. When I make a statement, capacitor generates reactive power, produces reactive power, inductor absorbs the reactive power. It is like intentionally projecting inductor as inferior to capacitor, correct or wrong? But both are behaving in the same way. It is taking the power and then giving back. Both the elements behave in the same way. There is no difference. So I generally don't use the word reactive power flows from grid to the machine. No, reactive power is always oscillating. Do you follow what I'm saying? So better you say reactive power support is established by the grid, right? When somebody gives, there has to be a person who will receive it. If there is no person to receive it, you cannot give charity. Oh, okay, I stop here. Boss is telling me to stop. I will continue.
If you want to continue, that's okay. That's my job to remind you that 5.
Correct. They also have to leave, right? So tomorrow I will continue after the lunch break. Thank you.